We're going to finish up this problem that we were working on in the last video. I had some technical issues, so I had to reset. But if you'll recall, let me scroll back up here. We were talking about creating a least squares regression line for an individual's birth year versus their life expectancy, where we were using the birth year as our X value to make a prediction about the life expectancy for our Y values. So, moving back to our problem, we had calculated our least squares regression line. I've gone ahead and copied it down here. Part G says to find the estimated life expectancy for an individual born in 1950 and one in 1982. So these are birth years, which means that these are both X values. These are both going to be X values. I'm just going to take those and plug those into my least squares regression line. So let's do 1950 first. Y hat is equal to 0.227 times 1950 minus 377.243. I'm going to grab my graphing calculator off to the side, 0.227 times 1950 minus 377.243. I ended up with an expected life expectancy of 65.407 years. And then I'll do the same thing for 1982. Let's do that in red this time around. Y hat is equal to, again, 0.227 times 1982 minus 377.243. So again, grabbing my calculator, 0.227 times 1982 minus 377.243, I ended up with 72.671 years. And I can actually go and check to see, hey, X equals 1950 and X equals 1982. Where do those fit in my data? So if I scroll back up and look at my data, we actually had here's 1950 and here's 1982, which means that they were actually included. And what you'll notice is that the predicted Y values might be a little bit different. They should still be relatively close to what we have here. But usually you can expect to see some amount of error within these predictions, because your line is never going to be a perfect fit. But they should be relatively close to the values that we're seeing in our table. So I'm going to scroll back down to finish up the last couple parts of this problem. Looking at part H, it says, using the least squares regression line, find the estimated life expectancy for an individual born in 1850. Again, this is a year, so this is an X value, and then it asks, does the least squares regression line give an accurate estimate? So let me scroll back up so I can see my least squares regression line. Remember, I'm just taking that X value and I'm going to plug it into this equation that I found in the last video. So Y hat equals 0.227 times my X value is 1850 minus 377.243. So one more time, I will grab my calculator, 0.227 times 1850 minus 377.243. And I end up with a life expectancy of 42.707 years, which at first glance seems awfully low, 42.707 years. The reason for that is I can look at this X value that I have. It's 1850. And I'm going to scroll back up, and I'm going to look at the data values that we used to create this. Remember, our X values are 1850, and if I look at the X values that I have right here, all of these X values, the lowest one I have is 1930, the greatest is 2010. Remember that we want to kind of stay in that range of data values. And what I'm noticing is that 1850 is significantly lower than even my lowest birth year of 1930, which means that our model is not necessarily going to be reliable. It's not necessarily going to be accurate for data values outside of this range. So this is an example of extrapolation because the x value that we're using doesn't seem to match up with the x values that we have here. It doesn't fall within that range. So no, I would say that it's not reliable or it's not accurate. So it is not necessarily accurate because an x value of 1850 is extrapolation based on the data that we use to create the model. Now, I did say not necessarily accurate because perhaps it is. We may have gotten lucky, but there's really no way for us to know because we don't have that data in front of us. We don't have data to compare it against. So we don't really know for certain. We want to be a little bit skeptical of that. Last question here. Part I says, interpret the slope of the least squares regression line. So, okay, the last part, interpret the slope. So the slope that we found here is that coefficient in front of x, and I can scroll back up so that we have it, 0.227. 0.227. So I always like to make that a fraction, so I'm going to put that over 1. The other thing is I don't really like to work with decimals that are less than 1 here. I think that's can be a little bit confusing. So just to make the interpretation part of this make a little bit more sense in the end, I'm going to multiply both my numerator and my denominator by 10. You don't necessarily have to do this, but I think it's going to make digesting the actual interpretation much easier for us to do. So that would be 2.27 and 10. So the thing that I want to remember is that slope is change in y over change in x. So change in the y value over the change in x. So it also helps to think about, well, what do x and y represent? X was your birth year, and y was the life expectancy. So what this tells me, I always start, when I'm interpreting slope, I'm always going to start by talking about the change in x first. So this says if x were to increase by 10 years, if someone was born 10 years later. So let's talk about this. For an increase in 10 years for birth year, we would expect the life expectancy to either increase or decrease. And for that, I'm looking at the sign right here. We had a positive 2.27, so life expectancy to increase by 2.27 years. So if I was born 10 years later, I would expect my overall life expectancy to rise by roughly 2.27 years based on the model that we have. Now, I said for an increase in birth in 10 years, I was just trying to use the language that we used kind of earlier on when we were talking about slope. There's a lot of different ways you can phrase this, and I actually think the way that I wrote this is perhaps a little bit confusing. An easier way to think about that is to say, if for an individual, let's say that. How about for an individual born 10 years later, and then cross this out. We would expect the life expectancy to increase by 2.27 years. I think that's a little bit easier to understand and kind of wrap your head around. If you were explaining that to someone else, I think it would be easier for them to understand the point that you're trying to make. But there's a lot of different ways you can phrase this. The initial way that I wrote that the first time isn't necessarily wrong. I think that this is just a little bit easier. So these problems do tend to be quite lengthy. We had A through I in this problem, but there's a lot of different skills that we can practice, and we want to make sure that we're feeling confident with most of these before we move into our quiz and our test.